Okay, so yeah, this is a good question to start off on. So there's a question on homework problem 10, problem 969. And basically, in this problem, you have a suspended block and a wheel, right? And this is a 1.5 kilo block, and it's released from rest, and the block descends as the wheel rotates. The tension is 9 newtons, right? So if the block has a mass of 1.5 kilos, right, and the tension is 9 newtons, then it's asking what's the kinetic energy of the wheel 2 seconds, right? Right? So there are a couple different ways to go about solving this problem. And what I'd like to do is ask you actually how you would go about solving this problem. Right? One is actually to start with a free body diagram of the block. And if you do this, right, the problem gives you the tension in the string, right? And it gives you the weight of the block, right? Conservation of angular momentum, that's one way of doing it. I would actually use conservation of energy and Newton's second law. So there are a bunch of different ways to do these problems, but I want to note what's the kinetic energy 2 seconds. So in general, right, conservation of energy is very useful if you have objects that move a certain distance, right? Because if this block drops a certain distance, I can tell you how much gravitational potential energy was lost by it. I can tell you how much kinetic energy was gained by it. And I know in this system that mechanical energy is conserved. Okay, so the change in kinetic energy of the block plus the change in kinetic energy of the rotating wheel is equal to minus delta U of the minus delta U of gravity, right? So that's one way of solving the problem, right? A second way of solving the problem is the work kinetic energy theorem. So if we just consider the wheel, right? If we just consider the wheel, right, the work done by tension is delta K of the wheel, okay? So what we can do from that is we can figure out how far this block dropped, right? And compare that to the work done by the tension. So the force on the block from gravity is constant, and the force of tension is constant. So the work done by the tension, right? The work done is just going to be, right, basically the integral of torque d theta, right? Or F dot ds. Okay. Everything making sense so far? For this problem, I think it's a very instructive problem, not because there's one way to solve it, but because there are actually many ways to solve it. And I don't want you to get hung up on saying, okay, there's one correct way to solve these problems, right? So I'm going to show you how to do it both ways. One way is I want to convert from delta t to delta h, okay? So in this, right, what we need to do is we need to understand under constant acceleration how far the block will have moved, right? So from your kinematics unit, you can remember that, right, the change in height of this block is just going to be, right, v0 delta t plus 1/2 a delta t squared. But in this case, the block starts from rest. So we can eliminate that, right? Therefore, delta h equals 1/2 a delta t squared. The acceleration is not g, right? Because the acceleration is due to the net force on the block, and the tension in the string is going to be counteracting the block. So what we can do from here is we can say, okay, if that's the case, if delta h is 1/2 a t delta t squared, you can multiply both sides by 2 and divide both sides by a. Then we get delta t squared is equal to 2 delta h over a, right? We know this, right? Because F net is equal to mass times acceleration, right? So how do we get the net force? Well, we have a free body diagram of the block, right? This is 1.5 kilograms times g, and the tension in the wire is 9 newtons, right? So the acceleration is 9.8 meters per second squared minus, right, the mass over the mass, 9 newtons over the mass. So the acceleration is 9.8 minus 9 over 1.5, 3.8 meters per second squared, right? And then we can say, okay, delta H is 1/2 a delta t squared. Let's just calculate that real quick. So that's 7.6 meters, right? And then, okay, so if delta H is 7.6 meters, and we know the acceleration, and we know delta t, right? We can calculate delta U is mg delta H. This is negative. And delta K is 1/2 m v final squared minus 1/2 m v initial squared. right? So that's method one for solving this problem. Okay. Method two is once I have delta H, right, I know how far the block dropped, and therefore I know the total work done. Is basically the integral of the torque d theta, right? Which is T cross R d theta, right? Now, what's great about this is delta H is the integral of R d theta, right? If I have a wheel and it moves through some angle delta theta, right? This is R delta theta. So I can rewrite this because the tension is always at a right angle to the radius, right? The tension of the rope on the wheel, right? This is a Newton's third law pair with the tension, right? This is the tension of the block on the wheel and the wheel on the block are third law pair forces because the rope is massless, right? So the tension in the rope is the same everywhere. So therefore, this is just 9 newtons times delta H is equal to 9 times 68.4 joules. Okay. So this is actually something that I think is really cool about energy conservation problems. Is usually there's multiple ways to solve them because you can calculate where the energy is going in, let's say, 2 out of the 3 places where mechanical energy is conserved. And then you don't need to do the final calculation. So I think this is a little bit instructive. It's also a little bit instructive to note how you can convert between the time that an object has traveled and the distance that it's traveled if all the forces are constant, because then the acceleration of the object will be constant, and then you can use your 1D kinematic equations to solve the problem, right? So I think the really tricky part is, in this problem, is that you're given a time interval over which the work is done, instead of being given a distance over which the work is done. And so then you need to figure out how to convert between a time interval and a distance. Make sense? So just to summarize real quick. Write down the total energy as the sum of the potential and kinetic energies, right? Determine that the potential energy, sorry, not the potential energy, the total mechanical energy is conserved. And 3, convert delta T to delta H via the kinematic equations. Okay, so right, delta H equals 1/2 A 0 delta T squared under constant acceleration. Okay. So I hope that was helpful. Does anyone have any questions about when is the weight of an object considered as a force of torque? So the weight can be considered a force of torque. You just have to be a little bit careful about it. So, for example, right, in this case, it doesn't give you the, in this case, the way I want you to think about this problem, yeah, so the way I want you to think about this problem where you have some wheel with a moment of inertia and some object with a weight is not that the torque, right, and this object will have a radius r, is not the torque is weight cross r, okay? That's true in this problem, but you don't know the moment of inertia, and so because you need to restrict omega, right, that in this particular case, the problem is that I want you to think about this in analogy to Atwood's machine, okay? Right? This does not fall at A equals G, right? Because the inertia of the wheel is, because the wheel needs to be accelerated too, essentially. So the way I like to think about it is that if this accelerates at G, you're basically converting from gravitational potential to translational energy. But if you add in the wheel, you also need to convert rotational energy. And the ratio between those two has to do with the moment of inertia of the wheel and the mass of the block. So that's why I want you to think about it more like Atwood's machine, right? Where you have these two balancing forces. So in this particular case that we just discussed, the weight of the object is a torque. Another common one for the weight of the object being torque that we're going to think about a lot is mass balances, right? So in this case, right, we can definitely calculate the net torque, right? The only difference is that the moment of inertia of the system is a little bit different. Another analogy here between this system and Atwood's machine is you have these two masses that are essentially balancing each other out. The way that it works in Atwood's machine is that the tension on these two ropes has to be the same. And in this case, what's happening is if this object is exerting a torque, right? So this object is exerting a torque this way, and this object is exerting a torque this way. And so the net torque ends up being the difference in the weights times the radii. Okay, so let me just quickly do that here. So if I'm just going to talk about the weights as W. So in this case, the net torque for a level object, right, is just weight 1 cross R1 plus weight 2 cross R2. But what happens is the cross products have opposite signs, and so this ends up being, let's see which one has positive torque, the red one, R1 minus Y2 R2. Right? So the net torque ends up being the difference in the weights. So yes, it's relatively common to have the weight of an object considered as a torque. There's one other problem that I want to get to, which was a problem on your homework that I want to discuss, because I ended up discussing a lot of different rotational motion problems on Wednesday. And what I'd like to discuss is inelastic collisions. And specifically what are called completely inelastic collisions. So completely inelastic means that the kinetic energy is 0 in the center of mass frame, okay? So in order for the kinetic energy to be 0 in the center of mass frame, it means that the velocity of all the objects in the system must be the same, right? Because if any two objects had relative velocities, then the kinetic energy in the center of mass frame would be non-zero. Because the center of mass would be moving at a different speed than both of the objects in the system. So for completely inelastic collisions, step 1 is always write down delta P equals 0, or P initial equals P final, okay? And usually, this means writing down, basically imagine we have some objects here, M1, V1, M2, V2, right? So then we can just write down, and then, so this is the initial condition. The final condition is going to be some mass with M1 plus M2 going at with some velocity V, right? V final. So Pi equals Pf becomes M1 V1 plus M2 V2 is equal to M1 plus M2 V final. Okay, so this is true for any completely inelastic collision. And from here, you can basically go on to say, okay, I can break this down. This is really 2 or 3 equations, depending on whether you're working in 2 or 3 dimensions. So you can go down to say, okay, M1, v1x plus m2 v2x is equal to m1 plus m2 v final x, right? And you can write down a similar equation for Vy. And so what you can see here, I hope, is that even if we're given the initial momenta of both objects, you can always calculate the final momentum of the final object, right? Because you have two equations and two unknowns. Basically, your unknowns are Vfx and Vyx. Or, you know, if you know the initial, so basically in this particular case, in 2D, you have two equations, which means you can have two unknowns. So you can not know, for example, the final velocity vector, right? If you know the final velocity vector, you can figure out what the two incoming masses were. If you know the initial and final velocities of everything. Or you can figure out the initial momentum of one of the particles, or you can even figure out, if you know the final angle, you can figure out the initial angle of the two particles. So I want you to think about, in general, I want you to think about momentum conservation problems as solving a system of equations. And so going back to that idea that if I have two equations, I need two unknowns to solve the problem. Most of the problems on the exam that I would give you would not be, for example, having unknown masses. That ends up actually being a little bit challenging, but maybe something more straightforward for inelastic collisions. Okay. Are there any other questions for either specific homework problems or review problems that were puzzling or might be helpful? One thing I really would encourage you to do is go and do homework 10 before the exam, because a lot of those problems are similar enough to exam problems that if you feel like you understand how to solve them, then you'll do just fine on the exam. Okay, I think the inelastic collision one was one that I really wanted to cover. There's another one that I covered a little bit in class, and I want you to understand it, which is a problem with collisions, which is conserving conserving px but not py. So in this example, I have let's say a train car here. I have a little cart, and on the back of my cart is a cannon that will shoot out, let's say, a 1 kilo ball. Yes, you cannot. Okay, there you go. So fire out a 1 kilo ball, let's say 45 degrees. And this cart has a mass of 10 kilos, and this shoots out at 10 meters per second. Okay, so in this particular case, right, when the ball fires, there will be an impulse in the vertical and the horizontal. But there's a surface here, right? And that surface can exert a normal force. Does somebody have a question? Okay. So Py is not conserved, and that's important. So what we do is write down Px is conserved, so we can write down the conservation of momentum for Px. And basically what we get is that, right, the initial momentum is 0. If we call this P1x and this is P2x, the initial momentum is in x is 0, then P final x1 is equal to minus P final x2. Okay? So if this is m2, so then basically if this is the speed, then P1x final is m1 v1 cosine theta, right? Or that's this angle. So this ends up being 1 kilogram, sorry, it's a little messy, 1 kilogram times 10 meters per second times cosine theta, which is √2 over 2. So this ends up being, right, basically 5√2 kilogram meters per second. So that's P1F. So P2F is minus 5√2 kilogram meters per second, right? And since we know the mass of object 2, so that would be minus √2 over 2 kilogram meters per second. So this is P2Fx over m2. Okay. So we went over that a little bit on one of the problems with a cannon on a merry-go-round, right? In that case, what we did was we took the in-plane component of the momentum and then converted that into angular momentum. This problem is essentially one step removed from that. So the first step is to figure out which components of momentum are conserved, right? So if the external force is 0 in any direction, right? So a typical example of this, right, is if I'm in a horizontal plane, right, if gravity is pointing this way, then yeah, momentum won't be conserved in that direction, but let's say I have some fireworks, right? So I have a rocket that's following some parabolic trajectory that separates. Px is conserved. And at the moment of the collision, Py will be conserved because the change in momentum due to gravity is going to be small over a small time interval. But that we'll talk about later. Maybe by the end of the class, maybe in a couple weeks, we'll talk about rocket science if we have some extra time. So just to summarize, when you're thinking about collisions, you want to break them up first into elastic or inelastic, or partially elastic. Figure out what your conserved quantities are, and figure out how to write down conservation of momentum component by component, and then figure out whether momentum is conserved for each individual component. For most problems dealing with inelastic collisions, all the components of momentum will be conserved. Either angular momentum will be conserved, or all the components of linear momentum will be conserved. And in this particular class, there are more advanced concepts where that may not be the case. But that's really what I want you to take home from this discussion about different forces and when are the external forces zero and how do you figure that out. No, kinetic energy is only conserved in fully elastic collisions. So the two limits that we talk about a lot are fully elastic collisions, where the initial and final kinetic energies are the same, and fully inelastic collisions, where the center of mass kinetic energy is zero in the final state, or the center of mass kinetic energy is zero in the initial state, which is what's true in this Cannon problem, right? So if you have two objects that start together and break apart, or two objects that start apart and get put together, that problem basically restricts the velocities of the two objects in a way that allows you to solve the problem with less information given. And for fully elastic collisions, you can solve the problem by using conservation of kinetic energy. So that's most of what I have prepared today. I did a lot of review yesterday. This will be posted automatically to the Canvas site for Zoom lectures. So you'll be able to look at it and review this as you go. I encourage you to look at the exam review if you feel like you need more practice problems. I think the homework problems are very good for this exam. The exam will be very similar to the homework and practice problems, maybe a little bit, maybe fewer steps or something that takes a little bit less time. But if you understand the homework problems, you should be very comfortable doing the exam. Okay, that's all I have. So in that case, good luck with the exam. I will be around on my computer during the exam times. If you have technical difficulties, please email me, and I will get you set up right away. I do have more time allotted than the 90 minutes for exam time, just in case it takes you some time to get Lockdown Browser set up and get the room clear check going, so that you have the full 90 minutes of class time prepared for your exam. Okay, well, study well, stay safe, stay relaxed, and I will talk to you all next week.